Okay, so let's start. So I sent an email around. My apologies, but there is something which my colleagues need me for, so I need to leave earlier. So today's class is going to be a shorter one, around 40 minutes. Okay, so, but since space-wise, I'm okay in terms of material, so it shouldn't really impact anything in the class. Okay, so, and by the way, office hours as usual in the late afternoon. So we had started on clocks and timing, like how's physical time maintained. So I'm going to continue that that topic. So so we were in early phases of kind of discussing this and why we need physical time, what the importance, and also let's dive into what clocks mean, what the characteristics are, and also if you think about a clock, fundamentally deep down, there are kind of two parts to a clock. One is some sort of an oscillator, and the other is some sort of a counter. And so oscillators provide us the frequency, and the counter is where you have some sort of representation appearing of the time, and then you'll have some sort of an implied mapping function which takes whatever the counter shows, and then you map it into some agreed upon notion of time. So like for example, the counter value on your microcontroller, you will have somehow you will map it to let's say Pacific Standard Time. Okay, and since so the frequency of the oscillator would relate to passage of time, so expressed in some sort of hertz, for example, and then there would be some sort of an offset that your counter will have relative to whatever we are saying. So when the counter value has something, then that corresponds to, let's say, 10 a.m. PST today. So these are the two things. And then kind of if you dive kind of deeper, there's a lot more complicated stuff which is happening. So the oscillator itself usually has kind of a couple of parts. So there are so-called passive resonators, so like tuning fork, crystals, these kind of things, which have a resonant frequency, which means that they like given energy, they like to kind of oscillate at a particular very well-defined frequency, or usually some harmonic of it as well. And then they are surrounded by some sort of circuitry, essentially amplifiers and some other analog circuit, which collectively give us a stable oscillating signal. And we need this because otherwise a passive resonator cannot oscillate on its own, and also it dissipates energy as any real resonator would. Then we have a clock driver, which is what takes that signal, which at this stage we have some sort of a periodic analog waveform. Clock driver kind of gives us what we think of as a clock signal, kind of a periodic digital waveform of some form. And that's what feeds into the hardware counter I referred to. And then at the software level, typical abstraction that you would see is that you can read what this counter is, you can write to it, but most processors also offer other types of capabilities, like for example, maybe you can say do an interrupt when the counter reaches a certain value, inform me when the counter is overflowing. So there are other capabilities that most hardware provide. Additional stuff that you would see in most processors, again, is that you may do stuff to this clock driver. So for example, oftentimes these clock drivers also have phase lock loops which can multiply or divide the frequency. So you can tell them that, okay, I don't really need the frequency which was the native frequency of the oscillator, but rather I need some multiple or some multiple of it, or in fact, in some cases, perhaps even fractional values. So there's a lot of features that kind of get exposed to the software. Now, oscillators care about frequency. They don't have any notion of time, right? I mean, they are just giving you a periodic signal, and really kind of the thing that you would care about them is how stable they are, okay? Because as long as something oscillates, and as long as I can say, and if it is stable, then we can always give a multiplicative factor between that signal and our universally agreed upon notion of time, which is the cesium atoms oscillation, right? So we can define that factor. So we focus on frequency, and frequency is how good the frequency is defined in terms of stability, which basically means how much error it is. And since we deal with very small numbers, so instead of talking about percentages, the idea these things are expressed in parts per million or parts per billion. So you would see things like I have an oscillator which is 1 ppm, which basically means that if it's a 1 megahertz oscillator, then it can have an error of 1 hertz in it. Okay, so 1 out of 10 to the power 6. Kind of things that you really care about out here is really what kind of waveform I have. There's something called phase noise, which refers to that how jittery the edges of the clock are. So I may have clocks which on average have a particular frequency, but every clock edge may have tiny amounts of error in it. Okay, so there are many different ways of looking at it. One of them is that how noisy the phase is. Okay, that is, if you compare it against a stable clock, you would see that the phase of this clock, the phase difference, is going to have noise in it. Clocks, on the other hand, when we refer to clocks, we really care about the time. So at this stage, by the time you get a digital signal, you start thinking in terms of clock period and what is timing. But more importantly, when we think of time, is when we are accessing one of these counters. Most of the time, processors have many counters, and usually what operating systems do is they will take one of those counters and kind of grab it for themselves, and this is where they maintain the system time, and then they will associate some sort of data structure within the operating system, which is updated based upon what this counter is doing, and then the data structure is what the software gets to see. And part of the reason there is this issue that counters overflow. So we don't have anything counter of infinite number of bits. So usually it will have some n bits, 64-bit, 128-bit, but eventually it will overflow. And therefore, what you read out of the counter really has two non-idealities in it. One is that it measures time not as frequency times time, but really as a quantized version of it, because things advance only on clock tick, so I cannot measure sub-clock tick time with it. And the other is they overflow, so I'm really measuring only things on the modulo 2 to the power n. So what we have out here is really sort of something which is incapable of keeping long-term time, so therefore you would have some support in the software, which is what kind of applications see. Otherwise, the applications would have to maintain the burden of things rolling over very rapidly. A 64-bit counter running on a gigahertz processor rolls reasonably frequently. You do, and most the kind of processors we are dealing with, 32-bit counters or maybe 16-bit counters, so they roll over very rapidly. So there are two things that sort of end up mattering by the time we are looking at the software reading this counter. One is the smallest increment which the software can read. So that's the precision of the time, that is smallest time interval which is measurable. So just because your data structure may say nanosecond, which in Linux it does, doesn't mean you actually have a counter which is capable of giving you a nanosecond precision time. It probably doesn't, okay? One should always kind of take those numbers coming in from the OS with a bit of a grain of salt, because their precision is dictated by what the hardware is capable of. And the other part is how accurate it is, which is how close the timer is to the UTC. Or more precisely, if I take this counter or whatever the corresponding shadow of data structure in the operating system, and then apply my transformation function to it, which maps this thing to the UTC time, then what is the offset? So my computer may say whatever 10 a.m. in reality it may be 10 a.m. 1 millisecond. Okay, so that offset is what we care about. And of course that offset can keep changing because my oscillator may be unstable. So even if I were to precisely set that offset to 0, which in itself is impossible to do, generally speaking, but let's say we were to do it, then after some time that gap will change, because again I'm comparing against the reference. So humanity has defined an average of some 300 atomic clocks as our agreed upon notion of what a stable oscillation is, and our oscillator is going to keep sort of shifting from that. And the oscillators you find in devices can be pretty bad. I mean, tens of ppms or even some 100 ppm. If you look at some of the processors, they have many sources of clocks. One very common source of clock is clocks which are built into the chip. They are nothing but an odd number of inverters in a chain, and that oscillates because if you think about it, an odd number of inverters in a chain are going to oscillate, and they are pretty, the nice thing is they are built in, they are tiny, they can get very high frequencies. The bad thing is they are very, very unstable. They could be thousands of ppm. Okay, so they are quite unstable, but they power up very rapidly. So your processor can begin to run, but you can no longer say, okay, that if the processor claims to be 1 gigahertz, but that 1 gigahertz may be 1 gigahertz modified by that, let's say 1000 ppm or whatever, 500 ppm. So it could be pretty unstable relative to a stable physical clock. So that's what's going under the hood. So we have oscillator, we have eventually some sort of a counter. That counter is then read by the OS. Within the OS, some sort of a virtual representation is maintained, and then that is mapped to the actual time, and then that's what your application sees. So for example, when you change, let's say, the time zone of your computer, it's not as if anything is being done to this counter. It's all sort of an offset which that function is using, which gets changed. Okay, there's nothing kind of deep down which is happening. It's kind of different from, let's say, the way it used to be on PCs and all, where within the BIOS you can go and set the timer and all. That was almost a second notion of time. There was a separate timer, which is there in case of PCs, the so-called real-time clock. But then once the system is up and running, it's basically, let's say, Linux or whatever takes over, and they maintain time kind of separately. So your BIOS settable time has really nothing to do with what sort of one sees later. Now, the question which is relevant to us is how good this time is that we see. So we already kind of saw that there are a couple of non-idealities that exist. There is rollover, which is easy to take care of. There is quantization, which is impossible to take care of, because if I give you a 1 megahertz clock, fundamentally you can only measure time as good as 1 microsecond. And then finally is the issue of stability, which is the 1 megahertz that I think is 1 megahertz is not really 1 megahertz. It may be slightly different, and it may be changing over time. So these are kind of things that you face. So what we perceive as the time from a clock is influenced by the variability in the clock itself. So that's the stability. By environmental factors. So there are a lot of things which can affect the clock's timing. Any thoughts on what might affect? So let's say I have a crystal oscillator, kind of stuff that we find in electronics all the time. What kind of thing? Okay, temperature is one. What else?
Voltage?
Sure, voltage, yeah. The voltage you supply, if the voltage is fluctuating, as it does in sort of any electronic, it will affect it. What else? Vibration, yeah, or acceleration more broadly. So if you put it onto, I don't know, something which is swinging a lot or whatever, or a car which is accelerating or things like that, time is affected. Of course, relativity tells us that too, but I mean, here it happens for non-relativistic reasons, which is simply that as vibrations happen or as things are shocked and all, there are minor changes in the mechanical dimensions of the crystal, which basically cause this problem. So there are many factors which result in the ambient conditions affecting things. And then finally, there is another source, which is we read the counters, right? I mean, so it's not, so if there is any perturbation, right? I mean, conceptually think of it, there is a counter which is maintaining time, you're reading it, and then your notion of time is the response returned by the read function. If there is jitter or variable delay or some delay in that, then by the time I get informed about what the time was, A, it is already old information, and secondly, even if I try to compensate, the path between us may be different. So now we don't realize it on a wall clock because our eyes see it, and we are just traveling, whatever, photons hitting our eyes. But just imagine, as a sake of a thought experiment, that our internal notion of time, wherever it happens in the brain, if there was different amount of delays happening at different points in time, then our perception of time is going to be different, even for the same clock, right? I mean, so now in software, it's much more evident, right? I mean, if I read the timer, then there could be, for example, in the midst of a read function, an interrupt handler may come in and cause a different amount of delay. So by the time the software knows the time, there is an additional error which has kind of crept into that. So perceived performance, so in a way, what we have is really a kind of a sensing problem, right? We are trying to sense time, and as with any sensor, we will have issues with quality of the sensor itself, which is within the sensor, within the clock, so to say. Environment comes into play, and how we read the sensor comes into play. Okay, all these three factors kind of come into this picture. So if we, within our system, the quality with which we kind of get access to the time depends upon how well the clock is set, how accurate and stable it is, what its frequency is, how immune it is to all those environmental stuff that we kind of talked about. And when it comes to kind of people talking about how good the clock source is and all, there are a whole bunch of metrics which are used, like for example, how accurate the frequency is. Maybe in some cases that's all I care about, the passage of time. Can I measure passage accurately? If I want to measure a 1 second duration, that's fine, but maybe I don't really care about whether the time reported to me is a good time according to, it corresponds to, let's say, UTC or not. So I may not care about time in a coordinate system. I'm looking really time as a passage. And this kind of brings kind of that there are really two aspects of time that our applications care about. One is measuring duration, and the other is relating it to some coordinate system, right? I mean, there's some time-related coordinate system, and we want to know where our system is in that. Okay, so these are two very different purposes where time gets used. So how accurate the frequency is, how stable the frequency is, and you can think of time counterparts of it, how accurate the time is and how stable the time is. Okay, and time stability kind of in turn depends upon frequency stability. So one way of thinking about this is that I have some clock which has a periodic frequency, which has a periodic signal frequency f0, and then what happens is that at any given point in time, that clock would have a real frequency, which is f of t, and then this gap is what we call as the error in frequency, and then this ppm that I refer to is really what its nominal frequency, the supposed frequency is, minus the actual frequency divided by the supposed frequency, and then if you want to do ppm, then you multiply this thing by 10 to the power 6. If you're doing ppb, you multiply by 10 to the power 9. And this error, because f of t changes over time for all these reasons, so this error actually changes, so frequency error changes over time. And this error can change kind of short-term scale, long-term scale. What I mean by that is you can measure this error over short time horizons and long time horizons. And some clocks are pretty good long-term, that is, they will measure a year pretty accurately, but they may have relative to another clock a lot more errors over a short intervals, right? So if you look at different time scales, you kind of look at how the spectrum of the error looks like. They kind of behave differently on low frequency and high frequency. Short time scale and high time scale. One of the things that sort of you end up facing is that if you look at a clock, so like when you display a clock signal on an oscilloscope, it looks like a nice little square wave. But if you kind of go deeper and compare it against a very stable source, you would see that the edges of the clock are jittery. Now, for just normal code execution, it doesn't really matter. So if all you care about is executing code, big deal. The problem comes the moment this code begins to interact with the physical world. So for example, if it is measuring the speed of something, or if it's two robots trying to come together in time to do something at the same time, it's at that point in time that these issues begin to matter. So for example, if I am making a device which is, I don't know, measuring the round trip time of a laser to measure the distance, well, these jitters are going to matter because I'm measuring very short time intervals, and as it is, I'm facing a quantization error, and on top of it, this little error might sort of, this jitter might come into play also. And this thing can happen for a variety of reasons, but certainly the clock source itself, the resonator itself, is part of the culprit, but it could also be that the clock information is being sent to me over some sort of a communication link. A very good example is that there are a lot of these GPS devices, and we all know that GPS gives very good time. Indeed, it does. Inside the GPS receiver, they estimate time, which is pretty accurate down to tens of nanoseconds relative to the atomic clocks of the satellites. The problem is most of these GPSs, they expose their information through a serial port. Usually that's the most common way. On that serial port, there is a very well-defined protocol, essentially a set of characters which are sent out. So the serial port is basically a UART. Inside the UART are buffers, and there is highly variable delay. Any guesses on how much delay a typical UART, like when you communicate with something over a serial link, how much delays do you see? Are they nanosecond, microsecond, millisecond, seconds? Thoughts? Huh? Yeah, tens of milliseconds, hundreds of milliseconds. Yeah, I mean, it could be as much as 100 millisecond. Okay, so essentially you have a 50 nanosecond or something like that accurate clock, but you're talking to it using a serial link, which is 100 millisecond type latencies and highly variable, tens of milliseconds variation, depending upon what the state of the buffer was at the time you were talking. Even more, even lower, whatever. Protocols or interfaces where you might think I have a finer control, like if you look at SPI bus, okay, with a very simple serial bus which is used in all, even there things may matter. So I was talking with someone and these guys were trying to do very fine time synchronization. So their processor talks to their radio using a SPI bus, which is, as I said, a very simple bus, data line in each direction and a clock line. And they were seeing roughly a half a microsecond of jitter in their timing. Okay, you might say big deal, but these guys were trying to do synchronize things down to 0.1 microsecond. Okay, so half a microsecond is a big deal then. And the problem that happens is that in some of these radios made by, in this particular case, it's a radio from TI, internally they have a state machine. And which state the state machine happens to be in when you begin to communicate with it matters. If it's a one state versus a different state, then the first bit that goes out may see a different amount of delay. So there's a whole bunch of internal things that may come in the way, and an otherwise accurate source may, just the way you talk to it may cause additional sort of problems. This slide summarizes kind of some of the very common metrics that are used for talking about clock signals. So what is the time interval jitter? So it basically says that if I look at one clock edge and then I look at the nth clock edge, then how much jitter would be there in it? In the sense, if I take two signals or multiple, if I run the clock multiple times and then kind of look at relative to some starting edge, n clocks ahead, how much spread would I see? And as you might imagine that this n matters because this is indicative of stability over what time interval. There's another one which is called period jitter, which is basically saying if I'm looking at periods, that is two successive edges again and again, how much jitter we are going to see in that. And then finally, there's this long-term jitter, which is basically saying after a long number of periods, what jitter am I going to see, and this is where kind of things begin to stabilize. So all said and done, the oscillators that we use in our systems really get binned or characterized according to these characteristics of frequency, accuracy, and stability. Accuracy and stability, which one do you think is easier to correct for? So you buy a oscillator, you're using it in your system, and let's say I tell you it has both these problems. It's inaccurate and it's unstable. Which one do you think is easier to compensate for? Huh? Accuracy, yeah, because it's kind of a offset calibration problem. Instability can change over time, and so you have to keep tracking it. Then you have all these other measures of quality like phase noise, spurious tones in the spectrum. Spurious tones in the spectrum refers to the fact that most oscillators also have harmonics in which they oscillate. So on your signal, I mean, your supposed 1 gigahertz clock, there might be harmonics which are, or subharmonics which exist. They are just very low energy, so you don't sort of see them very easily, but they can cause problems also. Size and cost, power consumption, how programmable it is. All of these are things that you might care about. For example, many of our systems we put into sleep, and you don't want the clock to become a hungry source. For example, like a lot of wireless sensors and these tiny devices, like even things like whatever, Fitbits and the like, they usually are heavily duty cycle, and you want to make sure that clocks do not become things. And the longer the duration you need to maintain time for, you need more stable clocks, but stability comes at a price. Very stable clocks could be extremely expensive or extremely power hungry. just to reinforce the point, this is kind of showing stability versus accuracy. So this is a clock which is stable, okay, but inaccurate. This is a clock which is neither stable nor accurate. This is a clock which is accurate. It's kind of hovering around the nominal frequency, but it is not very stable. And this is a clock which is stable and accurate. Okay, and what you really want is through mix of software and hardware techniques, really kind of be on the right hand side there. So a confusion which often comes is that both these parameters of a clock, how stable it is and how accurate it is, get quantified in terms of ppb and ppm, but they are different things. Okay, and then additional parameters. Okay, you buy the same. So there is a stability in the sense of, like, if I were to just if my clock were to remain unchanged, or what would happen? But there are other things also happen. I buy 100 oscillators from the same manufacturer. They will have tiny differences. Lucas talked about variations for computing, but you have variations in clock also. So these things are going to be slightly different. So there's going to be a spread there. And the other thing is clocks age. They are ultimately deep down some sort of a physical device, and all physical devices have some sort of aging mechanism, and therefore aging also happens. So all these things essentially, the point is that how unstable you are, how inaccurate the clock is, all these things change over time, are different from part to part also. We already talked about these, the factors which affect it, and this kind of a slide kind of summarizes what kind of thing, if you were to actually look at clock deep down, what kind of things you might see. So firstly, oftentimes there are temperature steps. Suddenly, for example, sun began to shine on that sensor node out there, and then there is kind of a rapid change in temperature. That would affect over a very short time interval what is happening, what clock frequency you are seeing. There might be a vibration faced by that sensor, so that might cause changes in the frequency. Then there's short-term instability, which is always there. This is just kind of a normal part of these devices and all. Then you may have issues like the oscillator may be turned off and on. It's not like when you power something on, it just instantaneously reaches its good frequency value. It takes some time to stabilize, and that in itself would be milliseconds. So one has to kind of design that carefully also. And then there might be this long-term trend because of the aging. So all these factors come into play, and bottom line is that the clocks that you work with in these systems are not perfect. So now the thing is, are they good enough? And how good a clock do you need for different applications? So if you look across kind of applications that you might encounter, what I've shown out here purely just in terms of the stability dimension, what is needed typically. So if you're just running a microprocessor code and all, okay, I mean, you can tolerate, if all I want to do is run Word or something, as long as it doesn't make 1 second look like a year, which it does sometimes, but who cares if it's 1 second versus 1.1 second? I mean, even you can tolerate a lot of instability. And likewise for things like video clocking and stuff like that. Then once you start getting into things like Ethernet and all, then you need more stability, but you're still sort of 100 ppm or even higher. By the time you start getting into high-speed stuff and all, you start needing more stable clocks. Test equipment and all, they obviously need to be even more stable. Underwater sensors and all, these things need to be really more stable because they're sitting deep down, and part of the problem. So why do you think in underwater sensors I may need more stable clocks?
Because they depend on inertial sense of navigation. They don't have access to GPS.
Okay, so they don't have access to GPS. So point is, they don't have access to a good reference. And the access to reference that they do have is through acoustic links. Acoustic links take a long time to communicate. So it's very hard to synchronize a sensor which is deep down in the water, even if it could communicate with some device on the surface accurately, okay, because you have a communication link which is long latency and very delay prone. So the way to kind of deal with this thing is that you compensate that by having much more accurate clocks. So if you so things sort of by the time you start hitting these, you are looking at stabilities which are now fraction of a ppm. And then if you look at GPS satellite clocks, astronomy, and all these guys are close to sort of 1 ppb type things. Okay, and then of course there are other applications where even finer stuff need. I think how good a clock do we need? I mean, it really depends on the application, and you give a better, more stable clock, there is some application waiting for it. Particularly, so who are the people who do you think need the most stable clocks currently? What application? Out behind the size this list. This is nothing relative to what those guys need. Not really. Medical stuff, I mean, is physiological signals are in millisecond scale.
Large hadron collider?
Yeah, so particle colliders. Okay, in fact, the most advances in time synchronization and timing technologies are being driven by CERN. Okay, so they have this 26-mile thing, an atomic particle, whatever, splitting here and something happening on the other side, and they need to know precisely what's happening. So those are the guys who are kind of pushing timing technology kind of in the craziest possible fashion. In fact, one of the topics for a short presentation is going to be the work they've been doing, which is pretty cool. And in fact, also errors in that can lead to illusory discoveries also. So a couple of years ago, they had apparently seen some particle traveling at faster than speed of light, and there are some physics theories which do suggest that might be possible. These are particles called tachyons. So, but then it turned out that there was a problem in their time synchronization. Okay, so and the thing is, they are dealing with picosecond type stuff. Okay, which is just mind-boggling. Now, a consequence of all this different type of requirements is that if you open up a current device like this is iPhone 3GS, you would see that it has many clocks in it. Okay, many clock sources in it to be precise. Okay, so it has a GPS temperature compensated crystal oscillator. So GPS is, as you saw, they kind of need a more stable kind of thing. Otherwise, they'll have to keep recomputing the rates very frequently. There is a very low frequency clock for power management. While the device is asleep, it needs to doesn't need very high frequency. It's not doing anything, and this needs to be low power. For the radio, there are actually a couple of clocks. So there is one which is again a TCXO, a temperature compensated clock, which is needed for very precise synchronization with the base station. Base stations tend to often have atomic clocks in them because they really you can lose a lot of bandwidth if different base stations basically don't have a shared good notion of time, because then their communications are going to kind of overlap. So the cellular network operates in a highly synchronized fashion within a certain frequency band. But then you do put radios to sleep, but while they're asleep, you really don't need that power-hungry clock, which is a high-speed clock. So then you can again switch to a sleep mode clock. Over here. And then finally, there is a clock which is driving the application processor being Apple's whatever A6, A7 type devices. So you see, even in a simple device like this, we have 5 or 6 sort of oscillators, and oftentimes it could be as much as it doesn't. And more importantly, these oscillators often come in separate packages and not sitting on your chip. So you see kind of them occupying precious board space, and then oftentimes their height is actually more than the height of the chips. And they also begin to constrain kind of the packaging. Okay, so these are all issues that are faced, and of course, I mean, smartphone is a very aggressive example where we have multiple radios, we have GPS, we have a lot of stuff going on, and what happens is, to keep life simple, what they do is they basically design these things modularly. You can see how modularly designed this thing is, right? I mean, everything on the board is just kind of separate function, and then to keep designs reusable and all, they basically have each one of them have their own kind of a local clock to kind of work with. It also lets them meet specifications whenever, like if you look at specifications for a network protocol and all, it will come with very tight timing requirement, how much jitter is allowable and all, and you have to kind of meet those. So by the time you are done with all of these things, you do end up pretty crazy set of sort of timing requirements. So just to show you how these things manifest out, so this is some work out of the NIST's lab in Jitter pattern notes. Okay, so but they describe an experiment which was done by researchers in the NIST lab, I think. So what's happening out here is simple. They took 3 watches. and they synchronized it at some point in time, and then they conducted an experiment over a number of days to see how their time changed. And what you see are, so these are kind of your usual digital watches, and you can see that, of course, if they had maintained the time as per UTC, it would have been stable, but the three watches kind of did very differently. If you look at time in days from start of the experiment, one thing you would see is that they kind of wander around quite a bit. It's not like that, oh, there is a constant sort of frequency difference and that's just going to go there. This frequency difference itself is varying quite a bit. And so the time error in seconds, you can see at times it grows and at times it falls, and all of it is because frequencies are changing because of a variety of factors in this thing. So what they then they would do is they actually estimate the, so going back out here, they estimate from these things what the drift was in the frequency. They compensate for it, and now once you compensate for it, then you can begin to see that I can make otherwise flakier clocks be more stable. So now by compensating for this thing, all these clocks are kind of meandering around the 0 point. I can still not do cancel everything out, because canceling everything out would mean I have basically, I know the precise changes in the frequency. So essentially what's happening out here is that we are fitting some low order polynomial, let's say a piecewise linear or quadratic or something, to kind of capture the trends in the way the clock is changing, and then I compensate for this thing. And this in effect is what let's say NTP, which is the protocol used on your computers to maintain time, does. It basically talks to some servers, which have atomic clocks. It periodically talks to them, gets a sense of how our local clock is drifting, develops a model of this local clock, and then subtracts it out. And when it subtracts it out, it doesn't change that hardware counter. What it does is it changes the mapping function. So what the protocol lets us do is it defines how much is the offset and how much is the drift relative to UTC, or relative to some agreed upon notion of time. And then whenever the application asks or whenever the software asks for current time and all, we apply this function, okay? And this function's parameters are what keep on changing, and deep down it uses sort of more sophisticated versions of these things to kind of do that compensation. So at the end of the day, what we have really then is kind of non-ideal clocks, and then somehow we need to compensate for these things, because were we to not do that with the kind of oscillators which we can affordably use, standard crystal oscillators, we'll see our computers diverging very, very rapidly and all, and it will not be good. We did see out here these things called TCXOs. These are temperature compensated. They can get you down to 1 ppm type accuracy, whereas standard stuff would be 40, 50 ppm, so 40, 50 times more unstable. These things cost more money and they burn more power. Essentially what they internally do is they have a temperature sensor, and by some careful calibration, they constantly keep correcting the frequency, so that in effect they constantly do this kind of stuff to get more stability than one would otherwise have. So one could certainly design these systems using TCXOs and get something more stable, still not enough for all the applications, but better than just using a plain one. So I talked about that odd number of of inverters, that's like 500 ppm, 1000 ppm. Standard crystal oscillators, 40 to 50 ppm, maybe 20 ppm. TCXOs, 1 ppm, maybe 0.1 ppm. There are, by the time you start hitting 0.1 ppm and all, these are like, if you attempt to buy them, you'll have to prove you're a US citizen and stuff like that. I mean, they start getting into even into technologies which are export controlled and all. And the simple reason is that fine timing is very important for ICBMs to kind of hit the target, so kind of doing long-term navigation and all. So that's the experiment with the stopwatches, kind of illustrating very nicely that clocks have instabilities. It can be compensated. If you look at kind of our embed type standard things, what you would see is that if I'm measuring time there, so these systems, unlike our computers, do not come with a high-level notion of time. All they give you are timers. And if you look and you measure time in terms of timers, and then you, as an application writer, have to kind of establish your own time coordinate on top of it. So if you simply read these counters and all, you would see that you clearly see that there will be an overflow happening. The counter reaches maximum value will kind of come down. And then again, just like the 3-watch experiment, this is a bunch of nodes, a bunch of wireless sensing nodes. And again, we start out with them synchronized, if you may, and we kind of watch their evolution kind of over time. So actually, in this case, what's happening is we are watching the evolution of 4 nodes relative to 1 node, which we said was some sort of a reference. I don't know what has happened over here. But what you see again is that they are kind of drifting in weird ways, again, because of temperature and all. And you can see these effects even very dramatically. A node which is inside an air-conditioned room versus one which is outside, you would see these drifts kind of very, very apparent and all. And they have implications because we put these nodes to sleep, we expect them to come up in time together, all those things kind of come into play as well. So what that leads to is that we have a whole bunch of clock sources, and the primary thing as far as a clock source itself is concerned is really about the stability. That's really what you care about. Accuracy, as we learned, we could compensate for by calibration. Stability is kind of a tricky thing, and that's what you pay for. So you have quartz crystals kind of stuff, you have TCXO, you have something called OCXO, oven control crystal oscillators. Literally, these are tiny ovens which maintain a constant temperature so that the oscillator maintains a good stability. Then you have atomic clocks. There are something called chip scale atomic clocks that you can buy and all. And you can see the price increases also very rapidly as sort of you pay for it. And you can easily get in this territory. You can, by the time you are TCXO, you are into dollars to hundreds of dollars. By the time you are here, you are from tens of dollars to maybe $1,000. And in this territory, it's very easily you can get into $1,000, $1,500 type clocks. And of course, you're not going to put them and pay for it. So what do? We synchronize them with something more stable. And that's kind of the other weapon that you have, which is you can have a very stable clock, or you can have access to a stable clock which is elsewhere across the network, and you kind of interact with that. So as I mentioned, today's lecture is going to be a short one, so I'm going to stop at this stage. So on Wednesday, we have a bunch of short presentations due. So again, as usual, please either send me your PDFs, and just remember, we have that little competition going for band, which I love, by the way, or if you're a single person team, or the Pebble watches, which are also pretty nice. Okay, so see you guys on Wednesday.